In this video, we are going to focus on solving systems of nonlinear equations algebraically. So our learning targets are to use elimination, substitution, and graphing to solve a system consisting of a linear and nonlinear equation. Also, our goal is to determine when a system consisting of a linear and nonlinear equation has no real solutions. Now, we've worked with linear equations for a while, but these are examples of equations that are nonlinear. You may have a quadratic, which is here. That's called a parabola. This is a circle. I'm sure you talked in geometry about the definition of the circle, which means all of the points on the circle are equidistant from the center, and that focuses on the radius. An ellipse is our third shape, and this is what's called a hyperbola. These last three shapes in our list are what you call conics. There are three ways that we are going to focus on solving a system of nonlinear equations. We're going to look at elimination, substitution, and graphing. For this specific example, I am going to choose substitution. And the reason that I am going to look at this method is because each of these equations is in the y equals form, which means it already has a variable that is isolated. Now, when I do substitution, I always write them next to each other. So I'm going to have y is equal to x squared minus 5, and then y is equal to negative x plus 1. I am going to take this equation on the left, which is already solved for y, and I'm going to substitute it into my other equation, which means I am going to replace this y value with x squared minus 5. Now my goal is to solve. So I'm going to move all my terms to the left-hand side. So that means I'm going to add my x over, and I am going to subtract my 1 over. Now, on the right side, that's going to leave me with 0 because my x terms drop out and my y terms also drop out. Now, on my left side here, I'm going to write these in descending order. I have an x squared, I have a single x, and I have a negative 5 minus 1, which is a negative 6. Now, my job here is to think about how I can solve this equation. Well, this is a quadratic equation, so we have two methods we can use. You can use factoring, you can use the quadratic formula, you could also complete the square, but I really like to factor, so I'm going to focus on that method. Let's see, now I have x and x. You're looking for two numbers that are going to multiply to 6 or negative 6 and add to a positive 1. Now, remembering my signs, this means I'm going to have one positive and one negative because a positive times a negative gives me a negative number, and this one means the larger is going to be positive. So I have a positive and a negative, and I'm looking for two numbers that multiply to negative 6 and add to 1. So I'm going to choose 3 and 2. And again, I always check. So 3 times x gives me a 3x. Negative 2 times x gives me a negative 2x. If I add them together, I get a 1x, and that is what I wanted here. I wanted a positive 1x. So I am good to go. Let's erase our check and finish solving. Now, in this factored form, I can solve by setting each of these binomials equal to 0. I'm going to subtract the 3 over, which is going to give me a negative 3, and I'm also going to add the 2 over, which is going to give me a positive 2. Now, when you're solving a system of equations, you are going to be focusing on ordered pairs. So currently now, I have 2 ordered pairs, and I know that because I have 2 different x values. So one of my x values is going to be a negative 3, and in my second ordered pair, I'm going to have an x value that is a positive 2. Now, because I have two different x terms or x values, I am going to have to substitute each back into my initial equation. So substitution's like a big circle. I'm now going to take this -3 and I'm going to put it in here. So that's going to give me y instead of x squared. I'm going to have a -3 squared minus 5. That's going to give me a +9 minus 5, or 4. So that means this ordered pair is going to be -3, 4. And my second one, if I substitute that 2 in, back into this original equation, which was y is equal to x squared minus 5, I'm now replacing that x with a +2. So I'm going to have a +2 squared minus 5, or 4 minus 5, which is -1. So that means my second value for my y is -1. So those are my two solutions. Now, I am kind of curious here. If I were to graph these two equations, are they going to intersect at -3, 4 and +2, -1? Well, I'm going to give this a shot. Let's say now I have my x and y axes, and this isn't going to be perfect, but we'll do the best we can. This first equation here is a parabola. So in order to graph this parabola, I know that I am going to start at -5 on my y-axis. So I'm going to go down 5. And focusing on this coefficient, the leading coefficient is 1, which means my parabola is a standard size. There is no stretch. So I'm going to go over 1, up 1 on both sides, because 1 squared is 1. I'm going to go over 2, up 2. Over 2, up 4, because 2 squared is 4. And I might keep going just to make sure I'm being accurate. I'm going to go over 3 and up 9. Because 3 squared is 9. So again, I'm looking at 1 squared, which is 1, 2 squared, which is 4, and 3 squared, which is 9. And I use that pattern to draw a nice, accurate graph. Now, it would be a little bit better if I had a graph patch, but we'll see how this goes. So I'm going over 3 and up 9. So my sketch here is going to look like this. And now I'm going to graph my second equation. So this second equation down here, this is a linear equation. It has a y-intercept of +1 and a slope of -1. A y-intercept of +1 and a slope of -1. So I'm going to go down 1 over 1, down 1 over 1, figure out what happens on the left here. And using a straight edge, it's going to look something like that. Now, I know it did it correctly, or I did it correctly, if these two shapes overlap or intersect at these ordered pairs. So if I look at it, I did 2, -1 over 2, -1. That's not bad. And my second one was supposed to intersect at -3, 4. Well, if I go over to the left 3 and up 4, that's not bad either. Now, usually I don't graph unless I have a nice graph patch. However, I think I did a pretty good job with my rough sketch. Let's take a look at a second example. Now, just identifying these functions, this first equation is what we call a circle. And I know it's a circle because it has both an x squared and a y squared term. This second equation is a parabola because it only has one squared term. Now again, we can choose elimination, substitution, or graphing. Well, elimination's a little bit different here because I don't have these same variables with the same exponent. This exponent being 1 does not directly line up. So let's say we do substitution, just like the previous problem. So let's think about that. I'm going to write them next to each other. X squared plus y squared equals 9. And this guy, x squared plus y equals 3. Now, when I do substitution, I'm going to look for something that's common. Well, one thing that's neat here is both of these actually have an x squared. So I'm going to take the first equation and I'm going to substitute it into the second. So I'm going to take this equation and I'm going to solve it for x squared. So in order to do that, I'm going to subtract my y squared from both sides. That's going to leave me with x squared equals 9 minus y squared. Now I'm going to take this binomial, the 9 minus y squared, and I'm going to substitute it into my second equation for x squared. That's now going to look like 9 minus y squared plus y equals 3. That gives me a quadratic, which again, I'm either going to factor, use the quadratic formula, or complete the square to solve. Well, I don't like to deal with a negative coefficient in my y squared, so I'm going to choose to move everything to the right side. I'm going to add the y squared over. I'm going to subtract the y over. And I'm going to subtract the 9 over. Now, that's pretty sloppy. But on the left, that cleans up. These drop out, these drop out, these drop out, which is going to leave me with a 0, which is what I wanted. Putting my terms in descending order, that is going to leave me with a y squared minus y, and this positive 3 minus 9 is going to give me a negative 6. Now, this looks similar to the last problem. I know I'm focusing on a y and a y. I'm looking for numbers that multiply to a negative 6 and add to a negative 1. So the combination I'm going to use is 3 and 2. 1 plus 1 minus, the larger is minus, so this is going to be a subtraction, and this is going to be an addition. In order to solve this, I'm going to set each binomial equal to 0. In the first one, I would add the 3 over, which is going to give me a y equals 3. And the second one, I'm going to subtract the 2 over, which is going to give me a y equals negative 2. Now, just like the other problem, you're going to end up with a set of ordered pairs. So this first y, my 3, is going to be in the second spot, and my second y, my negative 2, is also going to be in the second spot. So let's find the x coordinates that go with those. If I take this 3 and I plug it back in, I now have x squared equals 9 minus y squared. Well, that means I'm going to have to take my 3 and I'm going to square it. So that gives me 9 minus 9, or 0. Well, I have an x squared on the left side. So in order to get rid of a squared, I'm going to take the square root. Now, normally that gives me 2 cases, but the square root of 0 is 0. So I'm only going to write that as a 0-3 ordered pair. Okay, we have to repeat that same process with the 2. So I'm going to take this negative 2. I'm going to bring it over into my equation, which was x squared minus, or equals 9 minus y squared. I'm going to use parentheses. I'm going to put that negative 2 in here, and I'm going to square it. So this gives me a 9 minus negative 2 times negative 2 is a positive 4. And 9 minus 4 is 5. Now, this is my x squared. Well, again, if it's an x squared, it's a quadratic. I have 2 solutions. So if I take the square root of both sides, I'm going to have x equal both a positive and a negative 5. Which means this ordered pair down here, the something, negative 2, has 2 different cases. It's going to have a positive root 5. And then I'm going to also have a second one where there's a negative root 5, comma negative 2. Now, I didn't give myself enough space to graph these 2 functions, but it would be a nice idea for you to check them using Desmos.com. Now, Desmos is an online graphing tool where you can, Desmos.com, type in the 2 different functions and see where they overlap. The graphs are very clear, they are colored, and it's a great place to check your work. Here's a third example. I'm actually going to approach this one using graphing since I have a nice graph patch below. Well, identifying my functions, this first one I know is a circle. And I know it's a circle because it has two squared terms. It has a squared term here and a squared term here. If you have two variables that are squared, you're going to have what they call a conic. If the leading coefficient is 1, it is a circle. Now, that's a little bit beyond what I would expect you to graph right now. You will be asked to graph a circle, but not an ellipse or a hyperbola at this time. So let's look at our circle. Inside here, these represents a shift. This x plus 3 is telling me where I'm going to move left or right on my coordinate plane. So if it's an x plus 3, that means I'm going to be moving left 3. And if it's a y minus 1, this means I'm going to be moving up 1. Again, the value or number with the x tells me left or right, how far I move in that x direction. The value that is added or subtracted to the y is telling me how far I move in the y direction. So if I write this as an ordered pair, left 3 from the origin is going to be negative 3, and up 1 is going to be a positive 1. So that means my center point is over 3 and up 1. Now, if you look back in the beginning, if you were to plug this negative 3 in to this binomial, it would take me back to 0, which is no shift. And that's the same concept here. If you were to take this 1 and substitute it in here for y, that would take me back to 0 as well, where it is no shift. All right, so I have my center point. Now, the value on the right, this 49, I gave you a nice perfect square. This is going to help me find my radius. And you always take the square root of that value. So my radius for this circle is going to be 7. Now, that means from the center, I am going to move or place points 7 units away in all of the directions. Well, I'm just going to move vertically and horizontally. So here I have 1, 2, 3, 4, 5, 6, 7. I'm going to have a point here. Also up. That's going to give me a point here. To the left 7. 1, 2, 3, 4, 5, 6, 7. And down 7. Now I'm going to do the best I can to draw a circle. Let's say it's going to look like this. Not bad for freehand. And then I have my second function, which is a line. X plus y equals negative 1. All of the exponents are 1. So I have a y equals negative x minus 3. Again, my goal is to put that in that slope-intercept form. Here's my slope, negative 1. And my y-intercept is negative 3. You can also write it as 0, negative 3. So I'm going to graph that one in red. I'm down here at negative 3. And my slope is going to be down 1, right 1, down 1, right 1. Same on the other side. Now, let's see what this gives me with a straight edge. Now, again, this is kind of a rough picture. It's always better if you used a graphing calculator or Desmos. But if we look at where these intersect, I'm going to focus on this point right here, which is 1, negative 4, and then this point over here, which is negative 8, 5. So my goal now is to check if I have 1, negative 4 and negative 8, 5, are those possible solutions for this system? We can check these solutions by solving this system by elimination and substitution. However, I'm going to encourage you to go to that program or that website, desmos.com, and see if those are the points or ordered pairs where those two graphs intersect. Let's look at a fourth example. Now, I have a linear equation And I know that because the exponent for each of these variables is 1. And then down here, I have a quadratic equation. And I know that again because my exponent or largest exponent is 2. So we have a choice: elimination, substitution, and graphing. Well, I didn't give myself a graph patch, so let's say we choose, I'm going to do substitution. I think that's a good method because my variable y is already alone for each one of these equations. Okay, I'm going to take my binomial on the left, and I'm going to substitute that in for y in my second equation. Okay, so now instead of the y, I have negative 2x minus 7 equals negative 2x squared plus 4x plus 1. I'm going to bring everything to the right side here. Like I said before, I don't really enjoy factoring when the leading coefficient is negative. So I'm going to add the 2x squared over. I'm going to subtract the 4x, just kind of stacking my values here. I'm going to subtract the 1. And let's add down. All of these values on the right are gone. So on the left side, I have a positive 2x squared, a negative 6x, and a negative 8. This gives me a common factor, a GCF of 2. So let's pull that out. I have an x squared minus 3x minus 4 left. You can again solve this quadratic by factoring quadratic formula or completing the square. I'm going to keep going with my factoring. This is telling me that I'm looking for two numbers. One is going to be positive, one is going to be negative. The larger is going to be negative. So 1 positive, 1 negative. I'm looking for values that multiply to 4 that are going to add to 3. So 1 and 4 and 2 and 2. Well, looking at this combination, I'm going to choose my 1 and 4. 1 has to be plus, 1 has to be minus, the larger minus. So I'm going to put my 1 here and my 4. And again, you can go through and check. I'm going to keep solving. I have 3 values here. Each one I'm going to set equal to 0. I have an x plus 1 equals 0, an x minus 4 equals 0. This first equation is what they call a contradiction because we all know that 2 does not equal 0. Solving the other ones, I'm going to subtract the 1 over. That's going to give me x equals negative 1 as one of my x values. Adding the 4 over, that's going to give me x equals positive 4 as my second x value. Now, as ordered pairs, I'm going to have negative 1 in the first spot and positive 4 in the first spot. To finish this off, I need to find the y values that match with that. So let's go through and backwards substitute. I have my y is equal to negative 2x minus 7. In for those x values, I am going to substitute both negative 1 and positive 4. So I have y is equal to negative 2 times negative 1 minus 7, which is a positive 2 minus 7, or a negative 5. So when I was looking at negative 1 as my x value to substitute, that gave me a negative 5 as an output. Okay, let's repeat the same process with 4. I'm now going to bring my 4 over and plug it back into that original equation. My y equals negative 2x minus 7. I'm going to replace that x value with a positive 4. And that's going to give me a negative 8 minus 7, which is a negative 15. So when I used 4 as my input, I had negative 15 as my output, which means if I were to graph these two functions, my linear and my quadratic, they would intersect at these two values or these two ordered pairs. Example number 5. I'm going to be focusing on graphing here because I have this nice graph patch. Let's identify our functions. The first one here is a circle. I know it's a circle because I have two squared terms. Both my x and my y are squared. So let's graph this circle. There's no shift horizontally or vertically because there's nothing added or subtracted to this x and there's nothing added or subtracted to that y. Now, I know my radius comes from this number. That's a perfect square. You're always taking the square root. So for this circle, I'm going to have a radius of 5. And since there was no shift, that means my center is going to be at the origin. So if I make my center point at the origin, I'm going to go out 5 in all of the different directions, horizontally and vertically. And my circle is going to look something like this. Now, my second shape is a parabola. And I know that because it has only one squared term. When I analyze this further, I know it's going to be an upside down parabola. So let's look at the vertex. This is in vertex form. This is telling me how far it goes left or right. It's always the opposite. So I'm going to have the x component of -2. This value at the end is telling me if I'm going up or down. Since it's a -6, that means it's going to go down 6. So I have the vertex of my quadratic at -2, -6. Okay, my parabola is upside down. So the leading coefficient, though, is 1. So I'm going to follow that same pattern. 1 squared is 1. 2 squared is 4. 3 squared is 9. But since it has a negative leading coefficient, it's going to flip from opening into the positive y's to opening into the negative y's. So now instead, I'm going to go over 1 down 1, over 2 down 4, and over 3 down 9. So right 1 down 1, right 2 down 1, 2, 3, 4. I don't actually need to go any further. It's going off my graph patch. This is what my parabola is going to look like. Now, when I analyze those two graphs, I recognize that they don't intersect at all. So if there's no intersection point between the two graphs, that means that there is going to be no solution. There are no points that satisfy both equations. Okay, we have one last example. We are going to solve this either by elimination, substitution, or graphing. Well, when I look at this one, I actually think elimination is going to be the best method because for my variables here, they are stacked. I have my y squareds and x squares right above each other, and they each have the same exponent. So let's approach this by elimination. This is going to give me 2x squared minus 10y squared equals 8. 1x squared minus 3y squared equals 6. Now, the goal of elimination is that you're going to add the equations together, hoping that one of those variables will drop out. Well, if I add them the way they are, nothing's going to drop out. So I need to change one of the leading coefficients so when I add them together, the variable does drop out. Well, I'm going to focus on x squared. And I'm going to choose to drop x squared out because I only have to manipulate the second equation. My goal is to get these leading coefficients to be the same. Well, I currently have a 2, and down here I have a 1. So if I multiply this second equation through by -2, the variables are going to have the same leading coefficients, but opposite operation. This is going to give me a -2x squared, a positive 6y squared, and a -12. Now when I add them together, my x's are going to drop. I am left with a y squared term that has a leading coefficient of -4. And if I add down here, 8 minus 12, that's also going to give me a -4. To get my y squared alone, I'm going to divide both sides by that -4. It's going to leave me with a +1. Now, if there's a squared term here, a quadratic, it's mean I'm going to have two solutions. So in order to get rid of that squared, I'm going to take the square root of both sides. And anytime you physically take the square root, it's going to give you a positive and a negative solution, because really what you're looking for is what value squared would give you a +1. And both positive and -1 squared could go in this position. Okay, now when I look at my ordered pairs, that means that I'm going to have points that have a y value of 1 and a y value of -1. So let's go back and substitute. I'm going to start with my +1. Going back to either equation, it doesn't make a difference. I'm actually going to choose the second one because it has a smaller leading coefficient. If I take my 1 and I substitute that into this equation, that is going to leave me with x squared minus 3. In parentheses, I'm going to put a +1 squared equals 6. That's going to give me x squared minus 3 times 1, or 3, equals 6. Adding the 3 over gives me x squared equals 9. And taking the square root, again, is going to give me two different solutions. I'm going to have both a positive and a -3. Well, that means I have to look at an additional ordered pair that has a y coordinate of 1. I'm going to have a +3, and then I'm also going to have a second one with a y component of 1 that has a -3 for its x component. All right, now let's repeat this process where I'm going to substitute -1 in for y. I'm going to take this top equation, my x squared minus 3y squared. In for my y squared, I'm going to substitute that -1, or in for y. I'm going to square this -1, which gives me x squared minus 3 times 1 equals 6, or x squared minus 3 equals 6. And I'm at that same point, x squared equals 9. Taking the square root of both sides gives me a positive and a -3. So again, that means I'm going to have to double this ordered pair. I'm going to have a +3 with my -1. And I'm also going to have a second ordered pair where there is going to be a -3 with that -1. Now, that means that these two shapes, or these two equations, have graphs that are going to intersect at 4 points. 3, 1, -3, 1, and 3, -1, -3, -1. I'm going to go to Desmos.com myself, check out these two graphs, and see if they actually intersect at the ordered pairs that I found.